our investigation of acids and bases, we're going to study salt hydrolysis. And what that will allow us to do is decide whether salts from acid-base reactions will form acidic, alkaline, or neutral aqueous solutions. We know acid plus base gives salt plus water, and so we're going to try and determine the pH of the salt solution formed. They're considered neutralizations, but not all salts are neutral. It's going to depend on the strength of the acid and the base. Is it a strong acid or a weak acid reacting with a strong base or a weak base? So it involves hydrolysis of the resulting salt with water. So the equations we're looking at, we've had the word equation, and we can do a generalized equation where the acid is HA. Specifically, there's a replaceable hydrogen ion H+. In the base, there's the hydroxide ion OH-. The salt is ionic, and water here, we aren't looking at Kw from the ionic product of water. The amount of ionization in water is going to be negligible. And so, once you have hydrolysis, it's the relative amounts of the H+ and OH- that are going to determine the pH of the salt. So with the anion, the A- is the conjugate base of the reacting acid, and A can be hydrolyzed. So here, as it's being hydrolyzed, it's forming hydroxide ions. So the release of hydroxide ions increases the pH. It's going to be alkaline. Cation hydrolysis with non-metal complex cations, so NH4+, the NH4+ here in the general equation shown as M+, is the conjugate acid of the reactant base, and it can be hydrolyzed here in the equation NH4+ plus water gives me NH4OH plus H+. So if you're releasing H+ ions, the pH is going to decrease because H+ is acidic. And if we have complex ions, here we've got aluminum with 6 water molecules, and remember, you're going to get attraction of the delta negative of the oxygen towards the positive charge of the cation because of the difference in electronegativity in the HO bonds in water. And here you can see the water molecule at the bottom right looked at with the dipole, with the arrow, for point of the arrow being the negative end and the cross being the plus sign on the hydrogen. So what happens in the cation hydrolysis? On the left, just looking at one water molecule that is circled, and one of the water molecules, as you look at the right, has lost a hydrogen ion. And that's because you are attracting an electron from the hydrogen-oxygen bond, which is broken, giving the O-, which is attracted to the Al3+, and leaving you with H+. And here it is again. So if the hydrogen ion is released, you are decreasing the pH. And you can release more than one hydrogen ion. So on the right, shown that with 2 O- shown, and they're attracted to the Al3+, resulting in 2H+. You can get successive hydrolysis of the water molecules around an aluminum ion. You can also get other cations, and the diagrams here show Fe3+, with the same idea that a hydrogen ion is lost during the hydrolysis. So we can summarize some of this in a slightly different way, looking, as I mentioned at the beginning, at the strength of the acid and the base that are reacting. And the first row there, strong acid, strong base. The salt is sodium chloride. Neither ions are hydrolyzed, forming pH 7. A weak acid and a strong base, like ethanoic acid and sodium hydroxide, produces sodium ethanoate, with the ethanoate ion being hydrolyzed, and as we've seen, ends up with a basic solution. So a pH greater than 7. And just pause to read and look through the strong acid, the weak base, giving a pH less than 7, acidic, and a weak acid and a weak base, difficult to determine, but because it depends which of the weak acid or the weak base, which one of the two is fractionally stronger than the other. And we'll look at that in terms of the Ka and the Kb, the acid dissociation constants, in a moment. So, salts of weak acids with strong bases are basic. So almost you're looking at this and saying, oh, the stronger base is going to determine the pH of the salt that's formed. And salts of strong acids and weak bases are acidic. Here are some examples of both of those. The ethanoic acid, the weak acid with sodium hydroxide, and the strong acid, sulfuric acid with the weak base, ammonium hydroxide. And salts of strong acids and strong bases are neutral. Neither of the ions is hydrolyzed. And right at the bottom, the salts of weak acids and weak bases, the pH of the resulting salt depends on the magnitude of the Ka and the Kb, the acid dissociation constant, the base dissociation constant. If Ka is larger, the pH of the salt will be lower, an acidic salt. If Kb is larger than Ka, the pH will be higher, and that's basic salt. And so if we look at two salts here, ammonium hydroxide and ethanoic acid, strangely enough, their Ka and their Kb are virtually the same. And so actually here, the salt, because the acid dissociation constant, base dissociation constant are equal, the salt will be neutral. And then if we look at ones with different Kas and Kbs, and you have to know what they are, sulfurous acid, weak acid, and the Ka is 1.54 times 10 to the negative 2. Ammonium hydroxide, 1.8 times 10 to the negative 5. So sulfurous acid has the larger Ka here. And you can do a calculation. If you look, it says pH equals 7 plus a half of the pKa minus the pKb. So in the table, I've also given you the pKa and the pKb, and this comes out to 5.53, so that it's lower than 7, so the ammonium sulfite that is formed is going to be acidic. And the Ka the acid dissociation constant is larger, it's an acidic salt. Okay, thank you, and enjoy your acid-base studies.